So far, we have learned about nucleophilic acyl substitution reactions as important reaction types of carboxylic acid derivatives. What we know so far is that acid chlorides, for example, are the most reactive carboxylic acid derivatives, followed by acid anhydrides, and then esters, which in turn are more reactive than amides. Amides are the least reactive, and this reactivity trend is based on the electrophilicity of carbon of the carbonyl group and the leaving group ability. An intriguing point would be, or quest if you like, why can't carboxylic acids undergo nucleophilic acyl substitution reactions? Let's draw the structure of carboxylic acids and see what we can learn from it. So this is the structure, again, of carboxylic acids. Now, if we were to categorize this, if you like, or put this somewhere in this reactivity scale, it would be very similar in reactivity to esters. So that's very important to remember. Now, for one thing, carboxylic acids are acidic at hydrogen, so that's also very important, okay? The other thing, if carboxylic acids were to undergo nucleophilic acyl substitutions, they must leave, or they must lose actually OH as OH minus, which is the hydroxide ion, and of course that's not a very good leaving group. Now, if we put carboxylic acids near esters in this reactive scale, and knowing that esters can only react with amines to give amides with respect to the transformations of carboxylic acid derivatives. Now, if we want to do that, the same reaction basically, reacting the carboxylic acid with the same nucleophiles that can react with ester to give the least reactive carboxylic acid derivative, then we would do something like this. Then we would bring in an amine, but amines obviously, because of the lone pair on nitrogen, are basic. So that basic amine will prefer to take off or abstract this proton in an acid-base reaction. So the amine will actually deprotonate carboxylic acids. That's because that hydrogen is acidic, and because amines are sufficiently basic for this chemistry. So amines are basic, and of course this hydrogen is acidic, so that's really very important. So what would happen now is actually an acid-base reaction. An acid-base reaction to give the conjugate base of carboxylic acids, which is the carboxylate ion. Now, carboxylate ions are not actually reactive anymore in nucleophilic acyl substitution reactions because they are not electrophilic at that carbon. You can prove this by resonance very easily. So this is exactly what happens if carboxylic acids are treated with a nucleophile, and that nucleophile will most of the time be an amine given this reactivity scale. The amine, being a base, will take off this proton from carboxylic acids in an acid-base reaction. So this is exactly what happens, an acid-base reaction, giving the carboxylate ion, rendering them not electrophilic anymore, and therefore not reactive in nucleophilic acyl substitution reactions. So carboxylic acids, therefore, are not reactive in nucleophilic acyl substitution reactions. That's because they are acidic at this hydrogen. Also, OH minus in general is a poor leaving group for them, or for this to be Y if you like, or for them to lose this OH, they must lose it in the form of the hydroxide ion, which is a poor leaving group. And when carboxylic acids are attempted to react with amines in order to give amides, for example, an acid-base reaction would rather take place rather than a nucleophilic acyl substitution reaction. The bottom line here is that carboxylic acid are not capable, or they cannot undergo nucleophilic acyl substitution reactions as other carboxylic acid derivatives do. That's because they are acidic and because they contain abhor leaving group.